morning, everyone. I'm Felipe, and welcome to today's webinar on AI for engineering simulations from 2 minutes to 2 seconds. Today, we're exploring some exciting coming together of artificial intelligence and engineering simulations. First, allow me to introduce you to today's agenda. Our first speaker will be Jesper, business manager at EDRMedeso. He'll be starting our discussion today by exploring the significance of integrating AI into engineering simulations, as well as introducing you to EDRMedeso's partner, NeuroConcept. Following Jesper, we'll hear from EDRMedeso's CTO, Frode Halvorsen. He will introduce you to NeuroConcept itself and how it works through the aid of a visual demo that you can see how the software and the AI integrations work. Finally, we're very excited to have application and engineer at NeuroConcept, Bastian, joining us today, who will provide further insights into how to build models in NeuroConcept Shape. And yeah, we're ready to go. I ask all of you, anyone that has any questions, on your toolbar on the right, you will find a drop-down menu called questions. We ask you to post your questions there, and we will answer as many as we can once the presentation has ended. If we are unable to get through all the questions, or they are very topic specific to your own case scenarios, we'll make sure to reach out to you individually to answer any and all questions that all of you may have. And now, without further ado, I welcome Jesper to the virtual stage. Jesper, over to you.
Thank you. So why focus on AI for engineering? Well, if you look at McKinsey & Company, they've interviewed a high number of CEOs and what are their top 8 priorities. And with little interpretation, you could say that AI is for sure a part of the top 2 of their concerns. It's Gen IA, the start of something big, and then it's out competing with technology. We read that as you want to be faster to market, as one example. So AI is on everybody's minds and lips. Everybody's talking about it. So investing in AI, where would you place your bet? Well, a lot of companies have invested in the marketing part of it. We talk about graphics, we talk about text and that kind of thing. Invested into sales so that you could potentially make, let's say, more comprehensive and meaningful sales responses on proposals. It could also be within support, where you take your archives of all the knowledge gained over time in the company, you put on a large language model, and then suddenly it's very easy for both internal and external to do their self-support on this one. And then IT also have a lot of tools very easily available to help coding and that kind of things. Various co-pilots for various jobs you do within IT operations. But really, own IP in the companies, the products that's being designed and manufactured, that's a place where we think that a lot of companies, they actually forget to look into the possibilities of AI. Maybe because it's not a black box solution where just implement it and start having benefits. There's a bit of work to do there. We'll get back to that a little later. So how AI for engineering can help? Well, better products. If you increase the number of simulations, the use of simulations, you will get better products. It will also de-risk your sales, meaning that you can start testing before bidding. You can make virtual prototypes very fast, where you have a very high level of confidence before going into a tender situation. You can also increase the agility of the company. Let's say you release a product version 1, and it turns out that you forgot to do a couple of tests, and you actually need to do a new version as soon as possible. So you can easily respond to requests. It could also be responding to the market, asking for something new whatever comes out of it. Also, the next gen designs, I need to put this one off, next gen designs, meaning that you could do non-biased designs, because AI doesn't really take into account that we never did it like that, or we haven't done it like this before, and that's not how we do it in this company. AI goes into the design space and explores any opportunity out there, and we actually have seen a couple of situations where that has given some very interesting results. Finally, or not finally, but the next one would be that you would see a higher innovation. We allude to very fast simulations in the invite for this event here. You can see simulations going from 4 hours to 50 milliseconds, and at the same time, the use of simulation moving from the simulation and verification team to designers, meaning that if a designer can test a geometry that he or she doesn't really believe could be good enough to submit for a 4-hour test, if he could test it in 50 milliseconds, then you would become more exploring, and it would be more like a playground, and you would naturally get a higher innovation here. Sustainability, the good old one. Well, for sure, the better quality in products also means more energy efficiency, but also we can use less material when we start doing topology optimization to a higher degree than what we can do with today's CAE tools. If we turn it around and look from a business point of view, better products would lead naturally to a revenue growth. If we assume that better products would give you more sales, it would give you lower service cost as well, and your customer loyalty will also go up because you build good products, so the next one I'm going to buy will be from your company. De-risking sales will bring up your winning chances, meaning that your bottom line would also benefit a lot from this, as well as your top line. But also de-risking sales also means actually removing risk, and risk goes very much to the bottom line of a company. A more agile company would be what you could call the winning company, which is something most companies like to be. And the next generation designs that you would come up with would actually make you the innovative company. You would be the leader within your industry because you make the very interesting new products that actually suddenly have a better performance in whatever industry you're in. And the higher innovation also makes you a very interesting company for media. It could be for shareholders, for a lot of things that can be interesting for a lot of companies and industries. And finally, on sustainability, if you're on par after doing all these kind of things, and you're still on par with pricing, as an example, if you're the most sustainable one, then you would be the choice of the customer. So who is Neural Concept and what do they actually do? Neural Concept is our partner in the concept we call AI for engineering, and Neural Concept is a pioneer within deep learning for engineering. It's still a very young company. It's a 5-year-old company roughly. They have more than 60 customers currently. We know it's more because it's been this number for a while, and I know they close deals and we close deals. And it's very simple. What their mission in life is to change the way that we engineer products, meaning that they actually want us to use simulation much more, bring it closer to designers, and actually do a democratization of your simulation usage. The challenges that drive, you would say, the need for Neural Concept, I would assume that a lot of you could actually can see from your everyday work is these. It is that you need to work in a trade-off between building better and better performing products and really get higher and higher quality into your products. But at the same time, the expectation is that you do it in shorter design cycles. And that is two things that is not really going in the same direction, unless you somehow add some kind of, let's call it magic, you really accelerate in some areas. So conclusion is that using traditional CAE tools CAD tools as we do today, it has reached their limit. And to bring you further on into this topic, we now have Frode. So over to you, Frode.
Thank you, Jesper. So I will go a little bit, let's say, deeper into the technology, what it really is, and how it's working, before our partner Bastian will show you hands-on how it's actually working, and how you work with it in your everyday life. So if you go into the design and development of product, one way to describe the process is using the V cycle, where you on the left-hand side you have a kind of the design and specification from system and down to components, and on the right-hand side you have the validation and verification of these designs and concepts. I think looking into the future, AI will influence all these points, everything from helping us set up the architecture to validate the components. And the focus of today's presentation will be around the bottom of the V, around the kind of the interaction between the component design and the component validation, where we use a lot of CAE simulation today. One of the challenges down there is that there are typically different teams that are doing the designs and validations. So you have these interactions and these design cycles that might be quite time consuming. So what we want to achieve, and what we will show you today that you can achieve with AI connected to simulation, is that these design cycles can be reduced from something like weeks that we see some customers have, and down to just a few minutes to do a design iteration. And why is that possible, and how is it possible? I think that AI is helping us address some of the key challenges that we have always seen in the world of simulation. So I've been using and working with CAE simulation for close to 25 years now, and there are some roadblocks that has been there since the day I started. And the main one, I would say, is the speed challenge. The fact that doing a high fidelity, sophisticated, accurate simulation, for instance, in the field of CFD, that can take from days to weeks and even months to go from a proposed design in a CAD system to a simulated high accuracy result. And this roadblock is removed with AI. The next one is the multiphysics challenge. As you all know, most practical problems are of a multiphysics nature. There are flow, interaction with structures, thermal, structural effects, and so on. And in the simulation community, we've been trying to tackle those challenges for decades. ANSYS, our main partner on the simulation side, have been doing a lot of great acquisitions, so they now have the possibility to do good physics simulations in any domain, but coupling them together in a let's say a real world engineering project is still quite complex and time consuming. So what we can do with AI solutions is that we can feed the AI models with data from different domains and do the multiphysics connections in the AI model rather than in the CAE tools. And this will provide us a great advantage, as we will see. Also, kind of going back to the bottom of the V cycle, most companies that I talk to are very keen on giving the power of simulation and putting it into the hands of the designers so that you can do earlier validations and verifications of your design ideas. However, even with Workbench and all the improvements that has been happening in the user interface of the simulation tools, it's still quite complex, and you need expert knowledge to take advantage of that technology. As we will see in my quick demonstration in a few minutes, taking an AI model, you can deploy it and wrap it up in very, very user-friendly interfaces so that it can be explored and utilized by anyone in the company. It could be from a sales representative to a creative designer. And finally, some research indicates that we as engineers we spend 40 to 50% of our time on repetitive, not really value-adding tasks. And in the simulation world, that might mean that you set up a simulation model in the initial phases of the project, and then you can spend a lot of time over the next months or over the next year just doing repetitions of the same kind of analysis with new input data, new requirements, and so on. And that are tasks that is not adding much value, at least not compared to the extreme expertise that you as simulation engineers have. So what we want to use AI for is to train the AI model to do a lot of these repetitive tasks, and then we as experts, as simulation engineers, can do the more innovative, one-off, and really exciting work. So in the big picture, I think AI can do a lot of things for us going forward, but to be quite concrete, we are now focusing on these 4 main challenges. That's what we're going to share with you today. And how is that possible, and what's the foundation of AI here? So the basic technology that we will utilize is neural networks and deep learning. And from a numerical engineer or a numerical scientist or simulation expert, it might look and seem a bit scary, like a black box that you just get some predictions that you don't have any control over. But I would strongly recommend you to do a little deep dive into how neural networks really work and what they are, and you will see tons of resemblance with the standard discretization methods that we use in the world of finite elements and CFD. So it is really just a new numerical method that is growing in popularity because of the GPU hardware that is now available. The other side of that coin is the fact that Gartner is projecting that in the coming big wave of AI, the main input for AI model will be synthetic data. And synthetic data, that's data that has been created and generated by models like simulation models, statistical models, first principle models, and so on, which is the core competence that we in this group have. This means that we're moving away from just the first wave of AI, where we try to gather as much data as possible, deploy some deep learning on it, and see, okay, what are the connections that we're able to make from the data set, and what kind of predictions can we do. Now we're moving towards having much more targeted data sets for specific purposes that will result in much more targeted and controlled AI models. And those models we will use in our design workflows. And how does it work? On a high level, that Bastian will show you the details of in a minute. What we do using this synthetic data and the neural networks is that we take historical data or data that we generate and upload that to the model. So we give it examples of designs in the shape of geometries, and we train it to recognize the physical response, the simulation response on each of these geometries. So we can upload hundreds or thousands or tens of thousands of all designs with corresponding simulation and or test results. And the model will learn to make the connections between shapes, completely non-parametric, and the physical response. That means that whenever we have a new design that we want to evaluate, we can go directly from the shape, from the geometry in the CAD system, throw it onto the model, and get it to predict the quantities that we have trained it to predict, without going through the featuring, the meshing, the pre-processing, the solution time, and also in many cases the post-processing is completely automated. And this is how we're taking down the design cycles from hours, days, weeks to seconds. As soon as you have a new design, throw it onto the model, and you will get the predictions with the accuracy that you more or less have in your training set. So in practice, this means that simulations will be used a little bit different in the future. There's no free lunch, so we still have to do a lot of the dirty work. We still have to do the designs, or at least to a certain extent. I will show you how we can use generative design shortly. We need to do the simulations to have the data that enables the AI models to learn the relationships between a design and a response, a behavior. And we still need to do the training of the AI model. So all of this work kind of needs to be done upfront, and it requires investment in time and money, to be honest. However, when we have done that, we can deploy models that are super effective and very robust to use in the projects. So what we've been doing with simulations up until this point is that when we are in the product development projects, in the design phases, that's when we have been creating the complex simulations models and struggle with convergence issues and long solution times on our clusters or in the cloud these days. I think in the future, we will front load a lot of the simulation work. So a great portion of all the simulations that we will do in the future will not be done project specific necessarily, but will be done to generate data that we can use to train our AI models. And then we will be much, much more efficient when we are in the projects. And what are the consequences of that? The old design cycles where it might take weeks to do kind of a design, prepare for simulation, do the simulation, evaluate the results, come up with a new design, and then repeat the process. That process definitely limits how many designs we can evaluate, and it takes a significant amount of time. With AI, we have a pre-trained model that allows us to explore many, many more designs in a short time frame, and then maybe just do 1 or 2 confirmative simulations at the end. So that means that if you say that you start a project here with AI into the mix with simulation and CAE tools, you will get to the end result of your design project quicker, and the product that you will deliver will have a higher quality. So those are the 2 promises that we're giving on behalf of simulation and AI. The next wave of using AI in the world of simulation is to use generative design. And that means that we can train an AI model to understand our design space. So for a certain product, we can give it all previous attempts, good ones or bad ones, and it will learn how we design certain products. Then you can ask that generative AI model to come up with new designs within that design space. And it will easily generate hundreds or thousands of new designs, non-parametric, regardless of whether you're able to set up a parametric model in your CAD system. So here we can just spit out a lot of design, and the real power of AI comes when you connect that capability with these really rapid evaluations that we get from the previously trained models. That means that we can connect the generation of new results with quick evaluations, and it kind of finally takes us to a level where we are able to do real optimization and real multi-objective optimization, evaluating hundreds or thousands or tens of thousands of designs in a day, creating a Pareto front, and then using our engineering judgment on where do we want to be. So I have one quick example of that, and that is based on a Danish company, a customer called Danfoss, who are doing, among a lot of other things, valve designs and valve development. So they took their old simulation from the database and trained a model. And the model was able to predict both kind of the 3D fields from the CFD simulation, but also kind of derived results such as flow rates, pressure drops, lifting forces, and so on. And the accuracy was typically within 1%. And that's the accuracy level that we kind of, I would say, easily get with a decent design set. When that was done, a generative model was trained so that it could learn, okay, how are this design space typically explored by our designers. So you learn that into a model and connected it to the physics prediction model. Then a multi-objective optimization loop was run, assessing 750 different designs, and a new Pareto front was obtained. And the resulting performance from that one was 10% better than the design that they had without AI in the loop. So that's quite significant. Another case that we see a lot of interest around these days are kind of cooling and adjacent heat transfer cases, where you, in this case, we're looking at cooling plates for battery packs, where you have a lot of design freedom. You can have these channels go more or less exactly as you want to, but you want to get as much heat as possible out of the battery. And if you're a customer, or if you're a company producing products like this, you typically get different requirements from different customers and changing requirements as they do their, for instance, electric vehicle development. So based on this kind of set of pain points in the industry, Neural Concept has developed a vertical that speeds up this process tremendously. That allows you to explore hundreds of different designs, doing optimization for your exact conditions, and then spitting out and creating the geometry for that. And just to kind of illustrate the fact that this technology is purely data-driven. So it's not kind of any physics in it. So it doesn't, the AI model doesn't care where the data is coming from, whether it's coming from a structural simulation, a CFD simulation, an explicit simulation, as we will see here, or from test data. So it's purely data-driven. So here's a kind of an example from the other end of the spectrum, where a phone manufacturer was struggling with the drop test calculations. Doing drop tests are time-consuming, both to set up the model, get it to converge, and also to do the calculations. And you typically want to do a lot of different configurations, drop angles, and so on. So that was a limiting factor for this phone company, but they had a good database of previous simulations. So a model was trained, and as you see here, the full transient behavior of dropping the PCB with the different components on it were simulated with very good accuracy. So it can be used on anything from structural stress analysis, fatigue, drop tests, CFD, and any simulation that you need to do repetitively, one can say. So as my final point, I will do a quick demonstration of how this can look in practice. So when you have trained these models, there are a number of ways the model can be deployed. You can deploy it through an API, being quite technical, so you can access it through a Jupyter notebook. You could actually tie it into your CAD system, or you could deploy it, as we have done here, in a user-friendly web application that can be used by more or less anyone. So I'll just quickly show you how that would work. It's a valve case where we have simulated the CFD of a valve with different opening angles and different configurations and different inlet pressures, and it's predicting the key flow results. And the way that you would use that's combined showing the user friendliness of these solutions. The way that you use this is that you just export a geometry from your CAD system, and you can typically just drag and drop onto the app. It recognizes it, and when I click analyze, the geometry file is sent to the cloud where this model is resting, and a prediction is being done. And you can train the same model, to predict any results. So here we have just some CFD results, like the pressure distribution, the velocity, and turbulence. You can also see, okay, what happens if the inlet pressure is going down. So you have kind of all these kind of design freedoms that you would typically like to explore. If you want to test a different design, in this case a different opening angle, process is just similar. Export a different configuration from your design tool, drag and drop, analyze, and you have updated the results. So this is how easy, accessible, quite complex CFD results can be made through the use of AI. And that concludes my presentation.